In this part of the lecture, I will show you the third illustration of Monte Carlo simulations, and I will, using this type of simulations, I will show you some properties of Gauss-Markov theorem. But before we discuss this, I will walk you through some very basic regression functions that can be used in R. In this exercise we will use a data set from package mass, and the name of this data set is Boston. Here we have 14 variables and over 500 observations, and if we type help Boston, we will get here we will get documentation of this package. So in this data frame we have information about prices of houses in suburbs of Boston, depending on some characteristics. And here so in this exercise, if for instance we want to build a model that explains median value of owner-occupied homes, we can run a regression model of this variable against some other regressors. And this will be illustration how to use regressions in R. Now we will use the function that we already know, summary. And if we, for instance, we are interested in summary statistics for one variable, let's say variable age, we can type Boston age, and we receive summary statistics for that are minimum value, maximum value, the first, the third, and the second, which is median, quartiles, and also mean. If we, on the other hand, we will type summary Boston, we should get summary statistics for all variables. And here we have for age, for median value. So this can be used in both ways. If we want to compute correlations between our variables, we can use function cor. And here, we will get correlation matrix of all variables correlations between all variables. Obviously, this matrix is symmetric matrix. That the correlation between Z and crime, Zn and crime is the same as between here. Is the same as between crime and Zn. So it's nothing surprising. This correlation matrix is quite insightful, but if we want to make this, to provide the same information in a bit prettier way, we can use package called corrgram. So we install this package. I hope that's still, okay, and now we can use it. Library corrgram. And now if we type corrgram, Boston, we will get this illustration of correlation matrix. There are in the documentation, we can control what is plotted in lower panel, upper panel, on the diagonal. So for instance, here you can read the documentation of this package. But for instance, if we want to plot change upper panel, and we can use panel ellipse. It should work this way. Yeah, it's not so visible. Yeah, we create some plots that tells us whether relationship between variables is positive, negative, or zero. Yeah, so here it's quite, to be very fair, everything looks quite chaotic. Yeah, but I think that it's good to know about existence of this function, because we can generate really nice plots with this package. Now let's talk about linear regression models in R. Yeah. And yeah, let's start with simple regression with only one independent variable. Yeah, and in this, so suppose that we are interested how what variable? Yeah, so we have Boston. Yeah, once again, how the share of lower status of the population affects median value of homes, yeah, in suburbs of Boston. Yeah, so to study this, we can run this way. Here we provide first dependent variable, our left-hand side variable, and our regressor, yeah, our covariate, yeah, which is it. Yeah. So now, if we call command lm, which stands for linear model, then the linear regression model is estimated using those objects that we provide as inputs. Yeah, and here we provided two columns, med v from Boston and lstat from also the same data set, and now we can assign the result of this function to some new object model. Yeah, and notice that in R everything is an object. Even model, we have model. In fact, the result of using function lm is a new list. Yeah, because if we type isList model, you will see that in fact this is some list with some attributes. Yeah, and here we have several attributes that are computed during the estimation procedure. Yeah, and then we can basically call those attributes like coefficients. Yeah, if we type this, yeah, we receive the same thing that if we type model. Yeah, so those coefficients are the same. Yeah, also there are several objects like residuals. Yeah, then we have residual for each individual from our training, from our data set that we use for the estimation. Yeah, and the same. Yeah, so this is it. And also it's worth mentioning that here we could obtain exactly the same result with a more compact notation. We could type this and this only, type data Boston. Yeah, and this is our model. Notice that here, even though that we didn't provide any option that we don't want or we want to have intercept, this intercept was introduced here. And if we want to estimate the model without intercept, then we have to provide 0 plus, yeah, that on the right hand side of our econometric model, here we explicitly tell R to ignore the intercept, and then let's call it model 0, and then yeah, we have only one coefficient estimated here for LStat. Also notice that here, yeah, apart from estimates, we don't have much more information. Yeah, and to obtain some additional statistical tests, some of residuals, R-square, the measure of fitness, we can basically use summary for our model. Yeah, so this is the result of running a linear model, this function lm, and if we type, yeah, we have in addition to our estimates, we have standard errors, the tests for statistical significance, and yeah, and some measure of fitness. Yeah, so summary, yeah, works not only with vectors of numeric values, but also with lists, which is with lists that are objects. There are several basic functions that take models as inputs of those functions, and over here you can find the most standard functions, and apart from summary, functions that should be useful very often are coef or coefficients. This is the same. Yeah, and if we run coef model, we get exactly the same result as from running model $sign coefficient. Yeah, you see that it's exactly the same. Yeah, and yeah, both things are equally good. And also, what is quite convenient is function fitted. Yeah. Yeah, and this is it. Also, so if we provide fitted, this provides fitted value, but I think that it's only for the training dataset. So the dataset that we use for the estimation procedure, and also there is predict. It should return exactly the same thing as fitted, but it may be a bit more flexible, because it allows us to make prediction on datasets outside of a set that was used for estimation procedure. If we want to include more than one covariate in our regression, it's not different in R. Multivariate regression in R. So if we want to have not only one variable, but let's say that in addition to this we want to have how this median value varies with not only with LStat but also with age, variable age, then we just separate covariates with pluses. Yeah, and now if we type something like this, we'll have now new model. Yeah, with three coefficients, estimated coefficients, and with two variables. Yeah, and again, yeah, as a rule. Here also for multivariate regression, 0 also works. Yeah, so here we have this, and here we have only coefficients for two variables. Yeah, but let's focus on this, and here everything works in a very similar way. Yeah, that if we take summary of this model, yeah, this summary command works exactly the same. Yeah, just like for a simple regression model. Now suppose that we want to introduce some non-linear transformation of our variables, yeah, and to illustrate this, let's use this example, yeah, and let's say that we want to study the impact not only of age, but age and age squared, yeah, and as you can see, R ignores all those transformations, yeah, and yeah, so it's not only that here we have age and age and some transformation of age. If we type this way, also this transformation will be ignored, and if we want to introduce this, we have to use function I. We write plus I, and in brackets we provide our transformation, and this function I tells R to use this transformation as it is. So it tells R, please don't ignore this transformation. Yeah. And here this is included. Obviously, yeah, as many transformations as we want can be introduced here. Yeah. So, for instance, scene age, also it should work. Yeah. So remember to use I if you want to make some transformations of your functions. Now suppose that we want to introduce the effect of interaction between two variables. The interaction in most cases is measured by a product of two or more variables, yeah, and if we want to include this interaction effect, we could basically here, just like here in this example, we can write this way, and let's say that this is model 1. Okay, but also there is more compact notation for this, that if we write variable on the right hand side, some variables with asterisk, and then R will include those variables plus product, and in this model formulas in R interaction, here we do it by hand, and in R interaction between two variables is written with colon. Yeah, so yeah, and in particular also, so this is if we want to introduce, we use this if we want to introduce those variables plus interactions. But if we want to introduce only those interactions, then we use colon. Yeah, and it should work. Yeah, exactly. So here we have on this product of those. Again, this is product of age and L-stat. Yeah, but written in our formula. It's not division, but it's a product. Yeah, so be careful about this. In the beginning of this part, I mentioned that I will dedicate this part to introduction to regression and to and then I will conduct Monte Carlo simulation to illustrate properties of Gauss-Markov theorem. But now I realize that it took 20 minutes to introduce for introduction to regression. So let's relegate this Monte Carlo and Gauss-Markov theorem to the next part. Okay, yeah, so sorry for confusion, yeah, and I hope that now we have enough knowledge to conduct this exercise. Yeah, so see you in the next part.